All right, so this unit goes back to kind of beginning of December-ish, okay? Late November, beginning of December. We started out this unit talking about simple harmonic motion. All right, so some things that we need to remember about simple harmonic motion are how it happens and what some of the examples of simple harmonic motion are. Okay, so first off, simple harmonic motion can happen if something is oscillating back and forth along a constant path because of a what? Because of a restoring force. Okay, so we have to remember things like, okay, oh, weird, hang on. Okay, so there has to be a restoring force. That's one of the key things. Okay, that restoring force has to vary linearly with displacement. Okay, that means the further from equilibrium the oscillator gets, the greater that restoring force becomes. Okay, that is crucial for true simple harmonic motion to occur. Okay, what were the two examples of simple harmonic motion that we talked about? Okay, mass on a spring and a pendulum. Okay, so we got to know those two as well. Okay, so okay, what things affect the period of a mass on a spring? The mass and the spring, right? The mass and the spring. So T equals 2 pi times the square root of m over k. Mass and the spring itself are the things that affect the period of a mass on a spring. Okay. For a pendulum, we just did the pendulum lab, so we know that the two things that affect the period of a pendulum are length and gravity. Okay. Should you expect to have problem-solving questions to do with both? Yes. Expect a pendulum question, expect a mass on a spring question. Okay. And expect a few multiple choice questions about restoring force and the nature of simple harmonic motion. Okay. Expect that as well. All right, then we talked about Hooke's law, and Hooke's law gave us a formula for restoring force. It was negative k times x. Okay, meaning that the spring constant multiplied by the displacement from equilibrium would equal the force in the spring. Why is the negative in there? Right, the displacement and the force are always opposite. If I displace a spring to the right, the spring pushes left, right? Okay, so the negative is in there in order to make sure our vector is always correct, okay, when we do this, this type of thing. Okay, units, remember, for K are newtons per meter. Okay, should you expect a Hooke's law problem? Yes, you should expect a Hooke's law problem. How is a Hooke's law problem going to be different from a law of conservation of energy problem? Right, a Hooke's law problem is only about one position. Okay, in conservation of energy, you have to compare. You always have to compare position A with position B. But in a Hooke's law question, it's saying at this displacement, what's the force? Or at this displacement, what's the acceleration? Okay, and the other thing we have to remember is that most of the time, this spring force is set equal to something else. Sometimes it's the net force. Okay, so sometimes it's negative kx equals m times a. So if a question's asking you about acceleration and it's got spring constant and displacement in it, and the spring's the only force, this is the situation we're dealing with. If we're dealing with a vertical spring, like Hooke was when he discovered this, okay, then he was saying that the force in the spring was equal to the force of gravity. And so he had negative kx was equal to m times g. Okay, those are some of the situations that we dealt with in class. All right. Now, one of the other things is, and this doesn't have to be true, but many times a Hooke's law question is not dealing with an object that's oscillating. It's just dealing with an object that is hanging, okay, or being pulled in one direction but not being released. Okay, when we're talking about conservation of energy, the object actually has to be oscillating. Okay, this is always going to be a freeze frame of a particular position. All right, questions on Hooke's law? All right, so conservation of energy. Okay, big point there. Okay, but it wasn't really anything new. We know that mechanical energy is conserved unless we're told otherwise. Okay, it's just that for a mass on a spring, we have to use a different form of potential energy. Okay, that is elastic potential energy. Okay, so if we're looking at, here's our equilibrium position. Okay, here's where the spring is. Okay, when the spring is at, the spring and the mass are at equilibrium. Okay, what kind of energy does the object have? Kinetic, and it's moving at its maximum speed. Okay, when it is here or out here, it would only have potential, because that's where its speed will be 0 and it'll be experiencing the maximum displacement or amplitude from equilibrium. So all of its energy will be potential. If it's anywhere in between, then it has some of each. Okay, so it's just like a roller coaster question, except instead of using mgh, you use 1/2 kx squared. Right? We did lots of problems like that. It wasn't something you guys seem to have much trouble with. Okay, but it's just review here, so just remember how that works, because there'll definitely be a conservation of energy problem on the unit exam. Okay, then we moved on to waves. All right, so we started talking about the properties of waves, and when we talked about properties of waves, we talked about the two kinds. Transverse and longitudinal. Okay, most of the waves that we've dealt with are transverse. Okay, light's transverse, water waves are transverse, waves in the spring can be transverse. Okay, we can also deal with longitudinal waves. Sound is the most common longitudinal wave that we dealt with. Remember, longitudinal waves are compressions and rarefactions. Okay, so it's in a longitudinal wave, the displacement of the medium and the displacement of and the direction of the waves are the same. In a transverse wave, the displacement of the medium is at right angles to the direction the waves are traveling. Okay, but in a longitudinal wave, okay, remember that the particle goes back and forth and the waves travel parallel to that. Okay, other things we talked about were terminology mostly. Okay, so if we're dealing with a wave, okay, the distance from here to here is one wavelength. Okay, so we talked about that. Okay. The time it takes for one complete cycle of the wave is the time for one cycle in anything is period. Okay, how many waves per second is frequency. Maximum displacement of the medium from equilibrium is, okay, height of the wave. What do we call it? Amplitude. Okay, things like that. That's all terminology we have to know, because it's terms that I'll use on the test. Okay, so if you don't know what amplitude means, and then I ask a question that says the maximum amplitude is this, you're going to be lost because you won't know what amplitude means. Okay, so make sure you know those bits and pieces of terminology. Okay, remember that the distance between any two equal points on a wave is one wavelength. It doesn't have to be from this equilibrium to this equilibrium. It could be from this crest to this crest, or from this point to this point. As long as they are two equal successive points, okay, the distance between them will be one wavelength. Okay, questions on wave properties? All right, then we talked about universal wave equation. It's not a difficult equation to use, okay? V equals F times lambda, or lambda over T, but of course it only appears like this on your formula sheet. And remember that there were a couple of tricks that we encountered to do with the universal wave equation. If I have a question that says 5 crests go by, how many waves went by? 4. Okay, review here. Don't know what happened there. Okay, that's 5 crests, but I start counting with the first crest. That's 1 wavelength. That's 2 wavelengths, 3 wavelengths, 4 wavelengths. Okay, if I tell you number of crests or number of troughs, the number of waves is always 1 less than that. If I tell you that a boat went up and down 4 times, that's how many waves? 4. Okay, because I told you it went up and down 4 times. That's 4 complete cycles. But if it saw 5 crests, that's 4 waves. Okay. All right, so that was one of the tricks. The other trick was to do with echo questions. Okay, if a question involves a sound wave traveling towards a cliff and back, okay, and it wants to know how far the cliff is away, remember, it told you how long the sound took to get there and back again. Okay, you only need to know how long it took to get there in order to figure out how far away the cliff is, or if it's a sonar question, how deep the ocean is, or whatever. Okay, but that was another one that caught a few of us because we forgot an echo travels there and back again. Okay. All right, so universal wave equation is important because there could just be universal wave equation questions, okay? But obviously it's part of basically everything else, about standing waves and all that other stuff that we talked about after that as well. Okay, interference, okay? Principle of linear superposition. Okay, these two waves are occupying the same place at the same time. What kind of interference is that? Destructive. What would the medium look like as a result of these two waves overlapping? Do they completely cancel? No. Okay, how do I figure out what this wave is, what this medium is going to look like? The answer is Coderre, you drew a really crappy diagram. Okay, let's say that this is +1 and this is -4, and this is +4 and this is -1. So where will it be? -3 here, yep. +3 over here, right? We add the amplitudes together in order to get the final waveform. I think I've told you a couple times, I guarantee you there will be a question just like that on your unit exam. Okay, you will have to identify the type of interference and draw the resulting waveform. Okay, waves at a boundary we just talked about the other day. So this is going to be, situational questions where you maybe got a diagram of a before and after kind of a situation. Okay, let's say it's a picture, something like this. Okay, this is a picture of a wave that encounters a boundary with another media. Is the second medium more or less dense than the first? Sorry, I drew that wrong. Done. It would help if Coder drew it right. There was no correct answer before. Okay, more or less dense? Less dense. Okay, it's less dense for two reasons. The reflected pulse is upright. It's the same as this one. Okay, and the transmitted wave is longer, which means it's traveling faster. Okay, that's the kind of thing you're going to be asked to do. Okay, so make sure you're looking carefully at that. Okay, it's mostly the reflected wave that tells you, but you can also tell sometimes by looking at the transmitted wave. The reflected wave is the most reliable though. If it's upright, then it's going into less dense. If it's inverted, it's going into more dense. Okay, so there'll be stuff like that. Okay, there'll be stuff on refraction, diffraction, reflection. Okay, all of that stuff, because that all happens at a boundary. There'll be lots of diagrams. Okay, showing that kind of stuff. You'll need to be able to identify what type of wave behavior is going on, okay, and things like that. So make sure you look over that stuff as well. Okay, because there'll be lots of diagram-related stuff in the multiple choice on this. All right, and then we talked about standing waves. Okay, so standing waves, remember we get those patterns, repeating patterns, okay, of waves in the medium. Okay, how many waves did I just draw there? Or how many wavelengths are there, sorry? 2, exactly, okay. There's 1 wavelength, there's 2 wavelengths. Okay, remember how we talked about if I tell you, yeah, here's the wave, you got a standing wave pattern that has 4 antinodes and it's 4 meters long, what's the wavelength? 2 meters, right? Because there's 2 waves here, right? Things like that are things you're going to have to be able to do, okay? So there could be some multiple choice kind of stuff to do with standing waves like that, okay? Or about why standing waves occur. They all have to be the same wavelength, same speed, same frequency, okay? Reflecting back and forth in order to build that standing wave pattern, okay? You need to know the terms, okay? This is an antinode, okay? This is a node. Other terms you'll need to know, fundamental frequency. Okay, that's F1. Okay, and so the second harmonic will be how many times greater than the fundamental? If F1 is 10, F2 is going to be 20. Remember, it's always a multiple of the first. Okay, F2 will be 20, F3 will be 30, F4 will be 40. Okay, it's always a multiple of the fundamental. Okay, and then we talked about air columns, which are just standing waves, but they're standing sound waves. Okay, remember we talked about closed air columns and open air columns. Okay, in a closed air column, okay, only one end is open. Okay, and at F1, this is the waveform that's in the tube. How many wavelengths is that? 1/4, which is where this formula comes from. Lambda equals 4 times the length of the column. Okay, with an open air column, okay, our fundamental frequency looks like this. Whoops, that didn't work out very well. Okay, how many wavelengths are in there? Half, right, which is why lambda equals 2L, okay, for an open air column. Okay, what else do we need to remember about closed air columns? When do they make sound? At Right, at odd numbered frequencies, okay? Because this is at F1, okay? But F2 looks like this. There's a node at the top. So while there's a wave in there, there's no sound, okay? F3 looks like this, right? We got 1 3/4 wavelengths in there. Or sorry, we don't have 1 3/4, we have 3/4 wavelengths in there, okay? And it's resonating, okay? So this is F2, no sound. F3, there's a sound, and so on. So we have to remember that closed air columns only resonate at odd numbered frequencies, okay? That could be something that ends up in a problem-solving question, maybe it's like a part B. Okay, questions on the air columns. Right. And then Doppler effect. Talked about that yesterday. Didn't seem to give us too much trouble. Okay, expect that there's going to be a Doppler effect problem on the in the written response, and probably 1 or 2 multiple choice questions about Doppler effect. Okay, what it is and kind of how it happens. Okay. All right. So remember, with Doppler effect, that's F equals F0. Okay, V over V plus or minus Vs. When do we add? When it's retreating, right? And when we subtract when it's approaching, right? That's really about all you have to remember, okay, to use that formula. Okay, so for the test. Okay, so there are 14 multiple choice questions. Okay, and they cover, you know, stuff about simple harmonic motion and energy. So there's simple harmonic motion and restoring force. Talks about, you know, simple harmonic oscillators and what affects their period. Then there's some wave properties kinds of questions, you know, like kind of what things can change when it goes into a new medium. Okay. Then some more wave form and property questions. Some of those behavior at a boundary questions, Doppler questions. Again, wave properties questions like frequency, wavelengths, diagrams. There's lots of diagrams. Okay. Standing wave terminology, and then more diagrams on wave behavior. Okay. In the written response, there are 9 problems. Okay. 1 to do with waveforms, okay, and interference, a air column, a universal wave equation, a pendulum, a mass on a spring, some energy, Hooke's law, Doppler, and a 2-speaker question. So that goes back to interference. I forgot to talk about those when we talked about interference. So let's just quickly talk about that again. Okay, so if I have a 2-speaker question, so I've got speaker A, speaker B, listener. Okay. Obviously, waves are traveling from the 2 speakers to the person. Okay. What determines whether they hear a loud sound or a quiet sound? Yeah, whether the point they're standing at is experiencing constructive interference or destructive interference. Okay, so how do we figure out whether it's experiencing constructive interference or destructive interference? The first thing we would need to know is the wavelength of the waves. The second thing we would need to know is these 2 distances. Once I know those distances and I know the length of a wave, I can figure out how many waves there are from the speaker to the person from each speaker. Okay, so if I have, let's say, 2 full waves coming from this speaker, and I've got 4.5 from that one, is the person hearing a loud sound or a quiet sound? So it was 2 wavelengths from one speaker, it was 4.5 from the other. Loud or quiet? Quiet, yeah, okay. Because if I go 4.5 minus 2, I get 2.5 wavelengths difference. That means that one of them is arriving as a trough, the other is arriving as a crest, because they are 1/2 a wavelength out of phase, or completely out of phase, okay? So there won't be any sound at that location. So we got to find the wavelength, number of waves from each speaker. It's the difference in the number of waves from each speaker that determines loud or quiet. Remember, on a problem like that, you have to show all the proof, okay? If you get there and go, oh, I don't remember to do this, I'll just write loud, and if I get it right, I get 5 marks. You're wrong. You'll get 1 mark for being a good guesser. Okay, you got to have proof, okay, to go along with that. Okay, all right. Questions from you guys? Anything you want me to go over in more detail? Okay, this morning on Google Classroom, I posted the review package for this unit. Okay, I would suggest that you probably have a look at that right now and see if that triggers any questions for you. Okay, I will answer questions the rest of class when they come up. Okay, but I'd say let's start working on the review package. I'll also put it up here on the board, but it's several pages long. I don't know why it ended up being that way, but it just is. So you can have a look at it and see what you need to ask about. Okay, so request for 2 speaker questions. Sorry it took me so long. Okay, so we have the following parameters for this 2 speaker question. The frequency of the sound is 500 hertz. The speed of sound in this room is 340 meters per second. The speaker setup looks like this. Okay, so I want to figure out whether this person hears a loud or a quiet sound at that location. Okay, so we said one of the first things we need to do is know how far they are from each speaker. So we have to do a Pythagorean theorem calculation right off the bat in order to figure out how far the waves have to travel from the other speaker to the person. Okay, so that'll be 4.65 squared times 2 or plus 2.2 squared, square rooted, and that's going to tell us that this side is 5.147 meters long. Okay, what do I need to know next? Wavelength. Okay, can I get that with these 2 numbers here? All right, so I'm going to use a universal wave equation. Okay, lambda will be V over F, so that'll be 340, okay, divided by I did that wrong. This whole thing's not going to work out because I did it backwards. Hang on 1 sec. Okay, sorry, we got to change. I'm going to just quickly change these distances here. Okay, so these distances should have been instead 2.15 meters. This one should have been 1.02 meters, okay? And this one here should have been 2.38 meters, okay? So same calculation, we still did Pythagorean theorem to get this one, okay? Now we're gonna find the wavelength, that's V over F. I just typed it in as F over V because I wasn't thinking, okay? So we get lambda being 0.68 meters when we do that. Okay, everyone all right with that so far? Okay, now that I know what lambda is, and I know how far the waves have to travel to the observer, I can calculate how many wavelengths there are between each speaker and the observer. Okay, so for this one, for 1.02 meters, that's going to be 1.5 wavelengths. I just go 1.02 divided by 0.68. Okay, and that tells me there's 1.5 wavelengths between this speaker and the person. So that's 1.5 like that. Everybody okay with that? Okay, then I have to do the same thing here. 2.38 divided by the wavelength, 0.68, and I'm going to get that there's 3.5 wavelengths here. So that's 1, 2, 3.5. Okay, do they arrive in phase? Yes, they do, because 3.5 minus 1.5 is 2, which is a whole number, which means they're arriving in phase, crest to crest, trough to trough. This person hears a loud sound at that position. Okay. Sorry, that took me so long and I screwed it up in the middle. Okay, anything else? All right, then let's get to work on the review package. Okay, hopefully that will generate a few more questions. I'm happy to answer them if they come up. Okay, so you got some time to work on that review package from Google Classroom.